dimensions. So in this lesson, we take the basic principles that we've learned so far in our trig unit and apply them to real-world situations involving triangles. So one of the things that we're going to have to deal with is something that we've already learned about using the unit circle and our primary and secondary trigonometric ratios, and it's the idea that I'll give for any ratio that we work with, there are actually two solutions within the unit circle for that particular ratio. So for instance, if we took the sine of theta at 45 degrees, we would get a ratio of 1 over radical 2. Well, we also get a ratio of 1 over radical 2 for sine way over here at an angle of 135 degrees. It also has a sine ratio of 1 over radical 2. So even within the unit circle here, there are two solutions. Now we're going to be dealing with triangles, and we're going to be working with obtuse angles. We're going to find out that there are two solutions if we just use our calculator, and yet in the real world only one of those will be the right answer. So our first definition that we have is on the ambiguous case, and that is ambiguous case. Ambiguous essentially means it's not made certain. You can't know for sure. We will be able to know for sure, but ambiguous means it's unclear. So it is a problem that has two or more solutions. A problem that has two or more solutions. Then when we are solving things in the trig world, we simply need to remember some of the tools that we've already learned about in past years. But we have first the sine law, which relates in a triangle the ratio of the sine of an angle to the length of its opposite side. So we have the sine of angle A, capital A, over lowercase a. So this is an angle and its corresponding side. And that ratio is equal to the sine of angle B over the length of side B, which is also equal to the sine of angle C over the length of side C. So if I just did a quick sketch here, that triangle looks too equilateral, but that's okay. You get the point. If we're talking about the sine of angle A over the side length of A, that's going to be equal to the ratio that is made by taking the sine of angle B over side B. And that's going to be equal to the ratio that is made by taking the sine of the third angle, angle C, over the side C. And you can take any two pieces of this equation in one to find one solution, and you need three of the four parts. So if you're using, for instance, these two, you'd need A and A, as well as one piece of this in order to solve the missing piece. Or you'd need B and B, and then one piece of this in order to solve for the missing piece. Okay? You can also use this the other way around. This is helpful to put in the numerator the angle if you're solving for an angle. If the problem asks you to solve for a side length, then you're better off using the exact same sine law, but now flipped, and we're going to relate the ratio of the side length over the sine of the opposite angle. And again, we just finish it out. Side C over the sine of angle C. And our last law that we need to remember is the cosine law. Cosine law is a little bit trickier, but you likely already have it memorized, and so just remembering it here won't be too difficult. But we can, in an acute triangle, we're looking for any side length. You can use this formula right here. Let's call that side length A. We know that A squared is equal to B squared plus c squared minus 2bc times the cosine of angle A. So the key thing to remember here, if you're memorizing it, is that your side length is opposite your angle at the very end of the equation, and the other two side lengths get squared and added up, and they're also right here. Okay, so each letter is twice, only the letter that you're looking for has its opposite angle in the equation. And there's certain times that you can use these and certain times that you can't use these, and certain times you can use cosine law but not sine law. Sometimes sine law is more beneficial if you have the right information than cosine law, and basically just remembering when and how to apply these laws. We can also use cosine law in order to solve for an angle over here. So we can rewrite this equation in terms of solving for the angle. Cosine of A is equal to b squared plus c squared minus a squared over 2bc. This is really just an algebraic rearrangement of this one, which we're not going to prove, but you can take it for truth. So there's the tools that we're going to be using today, and we're gonna dive into it. So before we get into our first example, we want a little bit more of a briefing on what this ambiguous solution could be, this ambiguous triangle could be. So we have this example, and you're going to try to draw two different triangles that could be the solution for this problem. We have a surveyor measures two of the sides and one angle in triangle ABC. She determines that side B is equal to 600 meters, side C is equal to 700 meters, and angle B is 45 degrees. Notice that two sides and one opposite angle are given. This is known as a side-side angle case. Go ahead on your own, try to sketch two different triangles that could satisfy the qualities of ABC. So go ahead and pause, and if you've done that for 2 or 3 minutes and you couldn't get it, then go ahead and hit play and check my answers. Okay, rather than give the answer, just going to quickly explain how I would do a problem like this. Always start with the angle that you know, okay? So I know that angle B is 45 degrees. I don't know this length, but that's okay. If it's too long, I'll erase it later. There's what I think a 45-degree angle looks like, and I know that's angle B. Now I know one of the other sides, one of the sides that I've drawn I know about, and one of the sides I don't know about. I know that, which means this side length, wherever it ends up being, is going to be side length B, which I do know, but I'm going to call this one my 700 meter one. I'm going to call this side length C, which equals 700 meters, and so I'm going to give that a point. And so that's point A, which makes this side A, which I don't know. But now look at what I can do with side length B. 600 meters I could draw here, or I could draw here. In both cases, this line is 600 meters. If you drew it to scale, you could, for instance, draw exactly 7 centimeters and use your protractor to get exactly 45 degrees. And then you would see that these end up being exactly 6 centimeters from this point to this line and from this point to this line. So I've drawn two different triangles, okay? One ends up being an acute triangle, where angle B is an angle C, capital C, is an acute triangle, and the other, where angle C is here, ends up being an obtuse angle. So there are two possible solutions. Part of what we're going to be doing today is figuring out which solution applies appropriately to the problem that we're given. Okay, All right, example 1, solve a problem using primary trigonometric ratios. We have Bazarudin. He needs a new rope for his flagpole, but is unsure of the length required. He can't climb up there and measure from the top down, so he needs to find a different way to do this. He measures the distance of 10 meters away from the base of the pole, as you have in your drawing. He takes 10 paces, and there you have 10 meters. He's standing at that unmarked angle, the 42-degree angle. From this point, the angle of elevation to the top of the pole is 42 degrees. And we need to find the height of the pole to the nearest tenth of a meter. It is safe to assume that the angle made by the flagpole on the ground is 90 degrees. So we're in a 90-degree triangle, and we can use primary trigonometric ratios. We're trying to find the height of the flagpole, and we already know this measurement, which is adjacent to the angle. So if I'm looking at my SOHCAHTOA for primary trigonometric ratios, I'm going to be using the tan ratio because I have the opposite and adjacent. So I know that the tan of 42 degrees is opposite over adjacent. I know the adjacent angle, the adjacent side length is 10 meters over 10. And I've named the opposite side length h. So all I need here is a little bit of simple algebra. I am going to multiply both sides by 10 in order to get h by itself. So now I know that h equals 10 times the tan of 42 degrees. Type that away on my calculator to determine that the height of the flagpole is approximately 9.0 meters. And to do this in your calculator, all you have to do is 10, tan, 42, enter. Okay? Another way to do it would be tan of 42, enter, and then times 10. But your calculator can do all this in a row. And remember, if you don't put anything here, if you don't put an operation in between these two values, it will automatically multiply it. So there we have the height of the flagpole. It's about 9 meters. B asks us, how much rope should Bazarudin buy? And justify your answer. Go ahead and think about that for a second. If you know anything about flagpoles, the rope needs to go all the way to the top and back down again. So we need to at least double this amount. And actually doubling it wouldn't be enough because you still need a certain amount to tie or wrap around or to make sure you have enough. So we're going to allow for some extra rope, and maybe 19 meters would be a good amount to buy. In example 2, we are asked to solve an oblique triangle problem. If you are not certain what oblique means, it's just a triangle that has no right angle. Okay? We have Patina, Quentin, and Romeo. They are standing on a soccer field. Quentin is 23 meters from Romeo. From Quentin's point of view, the others are separated by an angle of 72 degrees. And from Patina's point of view, the others are separated by an angle of 55 degrees. So here we're given two angles in one side length. And let's see which ones we're given if we draw this thing out. So again, I like to start with angles that they give us. So we know from Quentin's point of view, so I'm just going to go down here somewhere and draw Quentin. I'm going to start with a straight line because it's easy to draw from. And I can erase a piece of it if it's too long, and I can add a piece to it if it's too short. I know from Quentin's point of view, the others are separated by an angle of 72 degrees. So 72 maybe looks something like that. I don't know how long that piece is supposed to be, but we'll leave it like that for now. Quentin is 23 meters from Romeo. It doesn't really matter where I put Romeo It just means I need to pay attention to the side lengths that I'm drawing. I'm going to say Romeo is here. And I have one more piece of information. That means Patina is somewhere up here. I'm not going to put her up here yet because I don't know. She could be anywhere along this line, depending on what our angle is. From Patina's point of view, the others are separated by an angle of 55 degrees. So up here would be more like 60. Probably right around here. Again, your diagram doesn't have to be perfect. And she's got 55 degrees there. We had 72 degrees here. So there is our triangle. It's an oblique triangle because there is no right angle. And our first job was to sketch it. We did that. B, is it necessary to consider the ambiguous case? Well, we were told already that the ambiguous case is a side-side angle situation. So this is not an ambiguous case. We don't need to worry about it. B, we do not need to consider, the ambiguous case because we have two angles given. If two angles are given, it's no mystery what the third angle is going to be. We can determine angle R really, really easily. Angle R is equal to 180 minus 55 plus 72. So angle R is 53 degrees. Not ambiguous at all. Okay? C, determine the distance from Patina to Romeo to the nearest tenth of a meter. If there are two answers, which we know there are not, determine them both. This is just figuring out which law are we allowed to use. Can we use primary trigonometric ratios in this situation? Not a right angle triangle, so no. Can we use sine law? Well, we said for sine law I have to have opposite information and one other piece. So I can, and look, I'm actually trying to determine side length Q, the distance from P to R, from Patina to Romeo. So that's perfect. I'm going to use sine law. C, use sine law. Well, we're using angle P and side P, angle Q and side Q, and I'm looking for a side length, so I'm going to put my lowercase letters on top. I'm going to go with Q over the sine of Q is equal to P, lowercase p, over the sine of capital P. I'm going to insert the information that I already know, which is everything except for Q. So Q over the sine of 72 is equal to lowercase p, which is 23, over the sine of 55. From here, I can see that all I need to do to get Q by itself is multiply both sides by the sine of 72. That will cancel out those guys, leaving Q by itself on the left. And on the right, I will have 23 times the sine of 72 over the sine of 55. I can put that in my calculator in 2 steps. Okay, actually you can do it all in 1 step. You could do 23 sine 72 divided by sine 55, and it would come out just fine, as long as you remember to close the bracket that your calculator automatically will open for you. Or you could do it in 2 steps. Do the numerator first, hit enter, and then hit divide by sine 55, and you will get that the distance from P to R, the distance Q, is approximately 26.7 meters to the nearest tenth of a meter. So Romeo is about 26.7 meters from Patina. Again, we looked at our information, we had opposite information given, and we had the opposite angle of the side that we're looking for, so sine law was an easy choice for that one. In example 3, we are given that a lighthouse at point L is 10 kilometers from a yacht, a big boat, at point Y, and 8 kilometers from a sailboat at point B. And we're given one angle from the yacht. The lighthouse and the sailboat are separated by an angle of 48 degrees. Is it necessary to consider the ambiguous case here? Well, let's consider what we were given. We were given an angle Y, and we were given side Y. So we were given a side and its opposite angle, and then we were given not one other angle, but one other side. So because we're given side-side angle, we do need to consider the ambiguous case. So for A, yes, we must consider the ambiguous case. Yes, we must consider the ambiguous case because two sides and one opposite angle are given. Side, side, angle. Well, let's sketch those two possibilities. Again, we're going to start with the angle that we know, which is Y. I'm going to start with a flat line because it's easy to draw from. 48 degrees, something like that. That was angle Y. And we can go with angle L up here. That's going to be the lighthouse. From the lighthouse, we don't know the different angles, but we know that it's going to be, from the yacht to the lighthouse is 10 kilometers. 10 kilometers. And from the lighthouse to the boat is 8 kilometers. So we're remembering this can either be this line or this line. It could be 8 kilometers. We're going to draw two separate triangles. So we're told that this is the first possible position of the boat. We're going to call it B1. This length is 8 kilometers. And over here I'm going to try to draw the exact same situation. We've got 48 degree angle Y. We've got 10 kilometer distance between Y and L. And this time our 8 kilometers is coming down to form an acute triangle from L to the second possible position of the boat. So we are considering both of these situations, and in this case we aren't told which solution it's going to be. It actually could either be this picture or this picture, and we're asked to find, in C, we're asked to find the distance between the yacht and the sailboat. Okay? So it actually could be either of these solutions, and we don't know what it will be. Okay, so let's determine both of those to the nearest tenth of a kilometer. By doing that, I'll just keep going with this triangle's information here and this triangle over here. But we know right away we're given opposite information. Okay? That's my cue for using sine law. And then we're given one other piece. It's a little bit sticky here, isn't it? we're looking for the distance between the yacht and the boat, side length L, but we don't have angle L. So we just, again, we look at something that we can do. We find the thing that we can do. Well, I have side length B, 10 kilometers, which would help me get angle B. And if I have two angles in a triangle, I can certainly find the third angle, which would then allow me to use sine law again to find length L. So let's go through those steps here. We've got, we're going to first solve for angle B using the opposite information, side y and angle y. So we've got the sine of B1, sine B1 over side length B is equal to the sine of y over side length y. So the sine of B1 over 10, filling in the information that we know, is equal to the sine of angle y, which is 48 degrees, over side length y, which is 8 kilometers. And now I'm going to, well, I'll show you each step. We're going to multiply both sides by 10. And at the same time, I'm going to take the inverse sine of both sides. So what we're going to end up with is the measure of angle B1 is equal to the inverse sine of 10 times the sine of 48 over 8. Okay? Again, if you're good with your calculator and you've got your brackets in the right place, you can include all of this in the inverse sine. Otherwise, what you can do is just do the chunk in the brackets first. Again, making sure you've bracketed the 48 properly so that it doesn't give you the sine of 48 times 8, or 48 divided by 8, sorry, but rather the sine of 48 times 10 divided by 8. The whole thing divided by 8. Anyway, you can type that in your calculator carefully in one part or two parts or three parts, and you will find out that the measure of angle B in this scenario, this possible solution, is 68 degrees. Okay? All that. Now we have two angles, 68 degrees. We can find out what angle L is. Angle L is 180 minus, and there's two ways to do this. You often see me do it as I add the other two angles. Okay? You can also just go minus 48 minus 68, and you get the measure of angle L is 64 degrees. Now that we have angle L, we can use sine law to find side length L. If you have some space underneath, that's great. I'm just going to, you should have space underneath. I'm going to continue, I'll go underneath too. Get off of the beam of light here. So now I can use sine law again. We have the length of L is what we're going for over the sine of L. I'm not going to write in the formula that I'm going to use. I'm just going to put the information in. So the sine of 64 degrees is equal to, and whenever you're doing this, choosing which part of the equation to use the ratio that they gave you the exact information for in the problem. Okay, so I'm not going to use B and sine B because this 68 degrees is not exact. Okay, it's already rounded. So now if I use that rounded answer to get another answer, it's going to be a greater margin of error. So what I'm going to do is just use the information that they gave me. I'm going to use angle Y and side length Y, which is 8 over sine of 48. Multiply both sides by the sine of 64, so that the side length L is 8 times the sine of 64 all over the sine of 48. Again, you can do this in a couple of different steps or all in one if you're good with your calculator, but you will find out that the side length L is approximately, in this case, 9 9.7 kilometers. So in triangle option number 1, the yacht and the boat are 9.7 kilometers away from each other. To use the second triangle to find the second possible solution, the steps are essentially the same, but this time instead of first getting angle B in order to get angle L, we can use a little trick about ambiguous triangles, in which case angle B1 and angle B2 are supplementary, which means they add to 180 degrees. I'm not going to prove it in depth right here, but basically this was option 1, this was B1, and this is B2, and we've created a number of angles here. And actually, the angle that we have here and here are equal. We have an isosceles triangle here, right? Because they are both 8 kilometers, which makes the interior angles here at the base of the isosceles triangle equal, which makes angle X supplementary to angle O, and over here, angle X supplementary to angle O. So if angle O and O are equal, then X and X must be equal, which means that this guy over here, which in our diagram represents angle X, and this guy over here, which in our diagram represents angle O, they are supplementary. So instead of doing the whole using sine law here in order to find out what that angle is, I can simply say that B2 is equal to 180 minus B1. B1 was 68 degrees, so I know that the measure of B2 is equal to 112 degrees. 112 degrees. And now I can use the sum of interior angles to determine that the measure of angle L in this triangle is 180 minus 48 plus 112. I did my bracket thing again. I don't know why I do that. The other way is probably faster. It's definitely faster on a calculator. I find this faster mentally, maybe? I don't know. Anyway, angle L is click, 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 20 degrees. Put that in my diagram. And now I'm ready to use sine law to solve for the side length L. Side length L over the sine of angle L, which in this case is the sine of 20 degrees, is equal to, and again I'm going to use the known information, the information that they gave us in the problem, is equal to 8 over the sine of 48, which tells me that angle L is 8 times the sine of 20 over the sine of 48. Carefully punch that in our calculator, and we end up with length L being approximately 3.7 kilometers. So the yacht and the boat are either 9.7 kilometers apart, or they are 3.7 kilometers apart. And based on the information that we're given, we don't know for sure. It's the ambiguous case. There are 2 possible answers to this solution, and you need to have both of them. Alright, example 4, we get one example that they're forcing us to use the cosine law, which means we're not going to have enough information to use sine law, and it means that we're not going to be in a right triangle. So the radar screen at an air traffic control tower shows a Piper Cherokee 15 kilometers from the tower in a direction of 30 degrees east of north, and a Cessna Hawk 16 kilometers from the tower in a direction of 40 degrees east of north at their closest approach to each other. If the 2 aircraft are less than 2 kilometers apart, the controller must file a report. Our first task, as usual, is to sketch a diagram representing the situation. First thing we're going to need to kind of understand is
Cardinal
directions on a compass. We're given our directions in terms of north. So we can go ahead and draw north. And it's all from the perspective of the tower. So if I just go ahead and start like that, I know I'm on the right track then at least. And now I can draw what they see from the tower. So we have the skyhawk at an angle of 40 degrees from the tower. Let's say something like that. Don't know how long it is, doesn't matter. And then we have also the Cherokee is 30 degrees at an angle of 30 degrees from the tower. So it's a little less there. We know that the Cherokee is sited at 15 kilometers away. Let's say Cherokee, 15 kilometers and 30 degrees. And we have the Skyhawk, which is a little bit further away, but not by much. It's a bit too much. Skyhawk is 16 kilometers, and it's an angle of 40 degrees from north. I'll give you a second to draw that. It might be wise to use two different colors. We've labeled everything that we were given, and we can even go ahead and finish the triangle that we're going to be dealing with here. And that's side length T. Now, B asks, from the tower, what is the angle separating the two aircraft? Well, if one of them is 40 degrees from north and one of them is 30 degrees from north, then the angle between them must be 10 degrees. Okay? We'll call that angle T. For the sake of our problem, even though they could really all be angle T, but we're only going to be using this angle, so we'll call that angle T. And C, is it necessary to consider the ambiguous case? Well, we consider the ambiguous case when we're given side-side angle. This time, the angle that we're given is contained between the two sides. So we actually are given side angle side, in which case there is no ambiguous case. Okay? Basically, there's no other triangle that would satisfy this description. There's nothing else that would be, could be 15 kilometers and 16 kilometers and 10 degrees. Okay? Where C and S clearly end, the only line that can go across there is T. This angle is certain and this angle is certain. Okay? So no ambiguous case here. D, we are going to, will the controller need to file a report? So basically, if these two aircraft are within 2 kilometers of each other, the air traffic control operator in the tower needs to file a special report. So we're going to find out what T is. If it's greater than 2 kilometers, he's good to twiddle his thumbs and continue on his day. If T is less than 2, then we need to file a report. Well, to find out what T is, we're given side, angle, side. We have two sides and the contained angle, which means we're going to be using cosine law. Okay? Here we go. We're going to be using T squared, or you could use D squared for the distance between them. But at any rate, cosine law says one side length squared is equal to the other two side lengths squared minus 2 times the other two side lengths times the cosine of the opposite angle. In this case, it's our small angle of 10 degrees, which we found earlier. Well, let's fill in the information that we know. We know C squared is 16 squared S is 15, so we have 15 squared. And if you plug these in 15, 16, or 16, 15, it makes no difference. You're adding them. Addition is commutative. Minus 2 times 16 times 15. Again, 15 and 16 does not matter what order you put it in. And cosine of t, angle t, is 10 degrees. So notice it's a long formula, but the only missing piece is on the left side. And you have all the information on the right. So it's just a matter of typing things into your calculator carefully so that you do everything right. One of the biggest mistakes that people make in this scenario is they'll go in the calculator, they'll go 16 squared plus 15 squared minus this piece. Okay? If you do that, you've done subtraction before multiplication, in which the rules of math would be very angry with you because you didn't follow BEDMAS. Now, if you simply type this whole string into your calculator exactly as you see it here, your calculator will churn out the right answer, assuming that your calculator is in degree mode. Okay? Otherwise, you could do it piece by piece. You could do 16 squared plus 15 squared, enter, and then hit minus and do this whole string. But again, you need to make sure that you type it in properly, that you have your brackets, and your calculator will do it properly. Here we go. In our calculator, we end up with t squared equals approximately 8.3. Now we're not done. That's t squared. So what do we need to do? Well, we need to take the square root of both sides, which tells us that t is approximately 2.9. I don't need to worry about, we remember if you take the square root of a value, it could be positive 2.9 or negative 2.9, but why don't I have to worry about the negative value? Because we're talking about real world distances. I'm not going to have a negative distance between the planes. Okay? Okay, the aircraft are approximately 2.9 kilometers apart. Do we need to file a report? No. The controller does not need to file a report. Well, folks, there you have it. Your practice problems for this lesson are found on page 254, numbers 1 through 8. Enjoy.